This month, researchers will introduce a new tool called PAT, Prompt-Based Adversarial Attack, to attack pre-trained language models. They will discover that the attack transfers and that it works on completely different models that they have never touched. So this prompt-based approach isn't specific to one system, it's going to be unilateral. And 6 months from now, this problem will get its name, prompt injection. So let's dive in. On March 21st, 2022, a paper published under the name A Prompting-Based Approach for Adversarial Example Generation and Robustness Enhancement introduces PAT, the prompt-based attacks. The prompt-based attack in this paper will show us how to use prompts and mask and fill to slightly rewrite a sentence so that a natural language processing model will give the wrong answer. And it will work across many models because they share the same pre-trained foundation. The same idea can also be used during training to make the models more resistant to these kinds of attack. Before we talk about the attack surface, we need to understand what was being attacked. Here we have three types of models. We have BERT, CNN, and LSTM. BERT, which stands for Bidirectional Encoder Representation from Transformer, was Google's leading language model that used the new transformer architecture to understand the meaning of words by looking at both left and right of a sentence. That's why bidirectional. It became the foundation for many state-of-the-art systems in search, question answering, and text analysis. BERT also scored an 80.5% on the GLUE benchmark, which was a test to compare how well different natural language processing models understand and process human language. Next, we have CNN, which stands for Convolutional Neural Networks. It was a neural network that scans small groups of words in a sentence to detect important patterns or phrases. So if you had free money or very disappointed, it uses those patterns to classify the text, which is why it works well for spam filtering, review classification, and toxic comment detection. And last, we have LSTM, which stands for Long Short-Term Memory. It was a type A of recurrent neural network that reads text one word at a time, while remembering important earlier word, allowing it to understand sequences and context, and it was widely used for tasks like machine translation, fraud detection patterns in banking transactions, and the early models of voice assistants. Now, these models were actually deployed in production and they were making real decisions. So if you could fool them, then you could fool the systems that relied on them. In 2019, the first version of the paper that asked the question, is BERT really robust? A strong baseline for natural language attack on text classification and entailment? And the answer was no. They built a tool called TextFooler where they applied it to a sentiment task where an AI reads a review and decides if it is positive or negative. So the same way that Amazon, Yelp, app stores, or movie reviews would use to filter reviews. So let's take this sentence. The characters cast in an impossibly contrived situation are totally estranged from reality. So this is clearly negative and the AI gets it right. However, now we swap three words to synonyms. Contrived becomes engineer, situation becomes circumstance, totally becomes fully. A human will still read this as a bad review, but the AI now thinks that this is a good review. So BERT went from being 86% correct to 11%. Now the second task that was given was an inference task, and the AI would read two sentences and decide do they agree or contradict. Like what fact checkers and search engines would use, we have our first sentence where a person on a horse jumps over a broken down airplane. And then we have a second sentence that says the boys are in band uniform. AI will say that it contradicts because those are two completely unrelated scenes. Now TextFooler will be used and it will change the word uniforms to garment. So the boys are in band uniforms to the boys are in band garment, which has the same meaning, but the AI completely flips its reasoning and now agrees instead of contradicts. So BERT went from being 89% correct to 4% on this task. So the TextFooler searches for words that are semantically similar to humans, but slightly different in the embedding space. This tiny shift is enough to keep the meaning for the humans, but it will break the model's decision, because BERT learns from correlation and not true conceptual reasoning. And it wasn't just BERT, TextFooler fooled all three model types. the most trusted AIs of the time that was broken by a thesaurus. So the interesting thing is that TextFooler has a catch. Every synonym swap requires querying the target model in an iterative process. So we say, did that fool it? No, try again. Did that work? Still no, try again. Dozens to over 1,000 queries per attack, and each query will make a log more and more detectable. So part of the three problems is that you need to have direct access to the target, and in the real world, you don't usually have that. So the second problem is that the output isn't visible. So as we said, it would leave a log that becomes more and more detectable. And then our third problem is perplexity. How natural a text will sound. Ranges from 188 to over 1,300 will read just like broken English. So the question becomes, what if you could generate the same devastating attacks without ever touching the target? That's what today's paper is going to answer. And this is the key finding we open with. PET was able to fool BERT, but it also fooled LSTM, both natural language processing models with a completely different architecture. It was able to do this because it attacks the vulnerabilities at the language representation level and not the architectural level. If we recall on our second episode where DeepMind used their red team AI to query up to 500,000 against their target, well, PET needs 0. And because PET does not require querying the target model, an attacker can generate adversarial examples entirely offline, using any locally available pre-trained model. They can refine them until they work and then deploy them in a single pass with no prior interaction with the target model, making the attack very difficult to detect until it has already succeeded. So let's take a look at how PET exposes a weakness in a sentiment model using their attack surface, mask, and fill. We'll start with a normal sentence. The original sentence here is, the movie was absolutely wonderful and I loved it. If we send that to a classifier, the classifier will categorize it as positive. Now, the second thing that we'll do is we'll introduce a negative tone or negative mood trigger. So here we'll use, is it a bad movie? And this is going to lead the question or lead the context into being influenced. So here, next thing that we'll do is we'll add the trigger to a masked sentence. Is it a bad movie? The movie was absolutely masked and I masked it. Because the trigger carries a negative tone, BERT will read the trigger first and get biased negatively. Then it will fill in the blanks under that influence. So the output will be, is it a bad movie? The movie was absolutely wonderful and I hated it. And the next step that we'll do is we'll discard the trigger and keep only the filled text. So the movie was absolutely wonderful and I hated it. If we send that to the classifier now, it would be negative. So the trigger permanently influenced the masked words during the generation, and the final sentence now contains negative wording like the hated. And even after removing the trigger, the classifier will read this sentence as negative. To humans, the change may look very small or still natural, but in the model's embedding space, this small shift was enough to move it from the positive region into the negative region. And that's the vulnerability, because a boundary exists, but it can be crossed with minimal and fluent changes. So sometimes changing a few words wasn't enough to fool the AI, so you need to change too many words, and the sentence would stop making sense. So now let's take a step further. Instead of modifying the original sentence, we could leave it completely untouched. So we would use GPT-2 to generate a brand new sentence that would naturally fit a review. The original sentence here would be, the movie was beautifully shot with great performance. Using GPT-2, we might add something like, it also had a familiar quality that stayed with me. Then we would apply the mask and fill to this new sentence, and it would shift it from neutral or positive to negative. So here with the poison sentence, it also had a dull quality that haunted me. Now the final output to the classifier would just be, the movie was beautifully shot with great performance. It also had a dull quality that haunted me. The result would be negative. So instead of swapping words, we could eject an entire natural looking sentence that flips the model's decision. So here are the key differences between the two attacks between TextFooler and PET. So the first one is that the TextFooler swaps words from a thesaurus, and the results often sound weird. So a wonderful experimentation that I meticulously enjoyed. The human would read this and know immediately that something's off. And a security filter might even flag it, so this is more detectable. Now on Pat's side, the language model chooses the replacement words, so the outputs will read more like a natural language because the AI wrote it. The filters would have difficulties catching it, and no humans would even be able to notice it. TextFooler could be compared to a blunt instrument. It would be powerful but clumsy, but Pat is like a scalpel, so it's precise, invisible, and it doesn't need to access the target, more importantly. The same attack surface can also become the defense surface. We've seen how Pat can generate poison text that will fool the AI, but the researchers asked, what if we train the AI on these exact attacks? So we would take the poison sentences, show them to the AI during the training process along with the originals, and the AI will learn that these means the same thing, so don't get fooled. We can see results here on IMDb that the AI resisted 15% more attacks and only lost 1.5% accuracy on the normal text. The same story across every database. So we had a 10 to 15 points more robust with almost no trade-off. And as Dr. Feifei Mao puts it, we crafted malicious prompts to identify vulnerabilities. Then those prompts became training data, helping the AI resist similar attacks in the future. So the disease is the cure in this case. So back to the connection of the prompt injection. This episode, the prompting paradigm itself is the attack vector. So TextFooler proved these models were fragile, and Pat proved that you don't even need access to the target to exploit them. And because all of these models share the same learned pattern, the attack can be unilateral. So if you craft it locally, then it would work everywhere. This was 6 months before anyone coined the term prompt injection. This paper proved every principle behind it. We'll see this pattern again in PAIR in 2023 and in AutoDAN in 2024. Now, in this same month, another team published a comprehensive survey of adversarial attacks on NLPs, and they cataloged all the known vectors of the time. There was character levels, which is insertion, deletion, and swaps, word levels, gradient-based and portent-based, sentence level, adsant, adani, and multi-levels combinations. But there was no categories for prompt injection. The techniques existed as we just watched, but nobody recognized that there were symptoms of the same problem. So AI couldn't tell instructions from data. So we have 3 key takeaways. The attack was unilateral, it could be crafted locally, and it could work everywhere. The transfer would work because it would exploit patterns in the language itself, and then the defense that would come from the same mechanism as the attack. So the disease was the cure. The prompting paradigm was a double-edged sword. It would let you generate devastating and transferable attacks on a local machine without ever touching the victim. But understanding this mechanism would also give us an efficient way to patch the flaw. The feature that made AI more useful, which meant following the language, was also the feature that would make it more exploitable. As we've seen with the idea of the first episode, where the obedience would mean that it becomes more hackable, as we've seen in this month. So next up, in April 2022, we'll look at image generation that has a completely different medium, but it has the same vulnerabilities.